and moved beyond the place where we could apply some analytic formalism like perturbation theory. So I'm going to go back to my second slide of the first lecture to talk about the limited number of options that we actually have. And we've talked a fair bit about the perturbation theory. So what I want to do is spend a little bit of time talking about analytical models and almost all of the time talking about direct simulation. But I want to start with this idea of the Zel'dovich approximation to bring home one point. Let me remind you what the Zel'dovich approximation is. This is a situation where we can actually calculate exactly a nonlinear model. It's just not the nonlinear model that we're actually interested in. So in the Zel'dovich approximation, we assume that the particles all move in completely straight lines with their velocities fixed at the value you would get from linear perturbation theory. So in appropriately scaled units, they move with constant velocity. And this approximation defines a mapping from my initial or Lagrangian position to my final Eulerian position, which we've seen before in Lagrangian perturbation theory, except now I'm going to assume that this psi just grows according to linear theory growth rate from some initial conditions that we can calculate. And this can be written as the derivative of some velocity potential. And so this psi turns out to be simply related to the densities. If the initial field started off completely uniform at very, very early times, then the final density is simply the Jacobian of the mapping, because the proportionality constant is just a constant. So my final rho can be written in this form, where alpha, beta, and gamma are the eigenvalues of the Hessian matrix of this velocity potential, right? So this is a very simple thing. And if I ordered these eigenvalues alpha, beta, gamma, you could see that I would get a caustic crossing where two shells of particles would come on top of each other, and I'd have infinite density when d becomes 1 on alpha, then 1 on beta, then 1 on gamma. So qualitatively then, what this approximation tells me is that collapse takes place first along one axis to form a sheet, then along a second axis to form a filament, and then along all three axes to form some bound, point-like object. And so this is the sort of qualitative behavior of the Zel'dovich approximation, and it actually does a fairly good job of describing what we see when we look at the results of n-body simulations. So these are slices through an n-body simulation where the color coding is density. And if you look at the lowest redshift slice here at redshift 0, you see this sort of beaded filamentary network where these very dark dots here are collapsed virialized structures, dark matter halos, which we'll be talking about in some detail. And then you see some sort of filamentary behavior. Now, if I were to take the initial conditions of this simulation and apply the Zel'dovich approximation, I wouldn't get these tightly bound lumps. But qualitatively, this structure you see here, this filamentary-like network, would look very, very similar. And so what that means is that a huge amount of what we're looking at when we're looking at nonlinear structure is embedded in the initial conditions and then sharpened by some nonlinear mapping, right? Now, the Zel'dovich approximation is not quite right, but it is a nonlinear mapping that is sharpening up my initial conditions. And I'm going to come back to that theme several times. If you want to do more accurate calculations, you're more or less driven essentially to numerical simulations. And there's good news and bad news, and both of them are that our ability to simulate structure formation has increased tremendously in the last decade, right? So that makes us more powerful, but it also makes us more reliant on numerical simulations, which are somewhere between sort of theory and observation, right? We do experiments numerically, we try and gain insight from them. Mostly what they produce is numbers. Yeah.
Then the dynamics are not due to the gravitational forces, but more to the statistics.
Well, the dynamics is driven by the gravitational forces, but the largest scale structure you see is really almost present in the initial conditions, and it's sharpened up by that. So if you look at that kind of filamentary behavior, if you run that all the way back, you can basically see those patterns by eye in the initial conditions. So here's how one does an n-body simulation, and obviously this is somewhat schematic, but I begin at fairly early times, usually during matter domination, so late times by standards of a lot of what we've heard about, but in terms of linear time early on, and I displace the particles from some kind of initially smooth state, an initial grid or a glass or something, using either first or second order Lagrangian perturbation theory, so let's just say the Zel'dovich approximation. And then what I'm really doing with an n-body code is a Monte Carlo integration of the Vlasov equation, that's the collisionless Boltzmann equation, where each of the particles in the n-body simulation is some kind of Monte Carlo tracer that moves along the characteristics of the Vlasov equation. Now, the characteristics of the Vlasov equation just turn out to be Newton's equation, so that's just saying I move things with an acceleration given by grad phi, and the velocity time derivative is given by the acceleration, right? So that's straightforward. Typically, numerically, we have to soften these forces on small scales to avoid particle-particle scattering or integrating unphysically tight orbits, right? So I have these superparticles, they have no actual physical significance. They're Monte Carlo traces of my phase space distribution. I certainly don't want them orbiting each other, right? This is a planetary dynamics problem we're trying to solve here. So what I really want to do is approach kind of a fluid limit as I go to very large n, and as with any Monte Carlo problem, as n gets larger and larger and larger, my approximation to what I'm trying to do will be better and better. The interesting thing about n-body codes is they've been extensively developed over the last several decades using a variety of algorithmic tricks and so on, is that they scale pretty close to perfectly, up to a log factor. They're scaling almost perfectly, so it takes roughly twice as long to integrate 2 n particles as it takes to integrate n particles, and if you run them on twice as many processes, it runs about twice as fast. So these things have really, through a huge amount of work by the community, gotten to the point of being extraordinarily efficient codes. At the same time as all this has been happening, our understanding of, or to be more precise, our ability to describe galaxy formation has also taken fairly large leaps. Most of cosmology is really based on observing galaxies, right, in one wave band or another. But as we'll see, the fundamental unit of structure theoretically in all of these simulations will be the dark matter halo. And so in order to make any connection at all between observations and what we're actually computing, you need to work out how galaxies live in dark matter halos. And we increasingly understand that connection due in part to these simulations, in part to theoretical developments, but largely due to the fact that we now have extraordinarily large galaxy redshift surveys. The big problem always with galaxies is they have many properties which are highly covariant. And those properties, of course, therefore, have subtle correlations built into them, and you have to control those correlations very, very well in order to tease out the underlying physical correlations that you're interested in. And to do that, you need large statistical samples, and that's really something that's only happened in the last roughly a decade. So obviously, as with any numerical scheme, you have to go through and talk about numerical convergence and all of the issues that come up. There's a large literature on this. Obviously, this is something people have been doing for 20 or 30 years. The latest ones I know about are these 2 papers by Katrine Heitman and collaborators that came out just last year. So this is the latest in a long series of things. And I list some of the things here that you need to worry about in order to get all of this to work. One of the things that isn't normally emphasized is figuring out, you can run any cosmology you want, in principle, which cosmologies do you choose? As we become increasingly reliant on simulations, and as we'll see, a huge fraction of what we're doing now consists of multiplying fixed simulations together. Choosing which cosmologies to run is actually a fairly tricky one. This is a problem a number of other fields have wrestled with. It turns out the first 2 or 3 things you think of are dumb and shouldn't be done. So this is actually one of those cases where it's worth going and looking up the answer in a book rather than just trying to wing it. But there's also increasing realization by the cosmologists that we could learn something from other people here. And so this is something, for example, that the bomb people have been doing quite a lot of, because they run simulations of things too, apparently, it turns out. They're quite expensive, and people are extraordinarily interested in the answers, much more so than anything we do. So this just shows you an example. You could have picked one of 100 different plots to try and show this, where what is plotted is the matter power spectrum ratio to the probably famous or infamous gadget code, which is some kind of de facto standard in the community, and then -1. So this shows the deviation in percent of the matter power spectrum as a function of k for a 256 cubed particle simulation in a 256 megaparsec box. So that k of 1 basically shows you where you're starting to soften the forces and start to integrate things at the mean interparticle spacing. And I've only shown a subsample of all the codes that exist out of the literature, but as you can see for those codes, the agreement out to order k of 1 or so is at the percent level. So all of these codes were started from exactly the same initial conditions, analyzed with exactly the same analysis code. So this is just a test of that n-body evolution step. But you can see that basically everyone can integrate those equations relatively well, given the same initial conditions. And so that's at least encouraging, because in principle that should be possible, but it's not always the case that it is. The problems, of course, come as you move to smaller scales than what I plotted there. And as you go to smaller scales, you have to go beyond the pure n-body problem, which I'm claiming is relatively well understood, and include additional physics. Now, in principle, this isn't so hard. In particular, hydrodynamics, people often say, oh, you need to run a hydrocode. And running a hydrocode is actually relatively straightforward. This is another one of those cases where the first thing you think of is dumb. But you can, again, look up the answer in a book, and people have been doing hydrodynamic simulations for decades. So including hydrodynamics is actually straightforward, and there's many techniques that work. The problem, as always, is that there's physics coming in here. And if you actually look at what happens in the cosmological context, the gas cools pretty dramatically in deep potential wells. As it gets dense, it radiates very efficiently, reaches extremely high densities in a clumpy, multi-phase, turbulent, magnetized interstellar medium. At that point, it gets dense enough to ignite nuclear fusion, so it forms a star. The star gives off winds and radiation in ways we don't fully understand. They go supernovae in ways we don't understand. They inject momentum and energy into their surroundings in ways we don't understand. A bunch of them have active nuclei that are fed in a way we don't understand, and radiate in a way we don't understand, and do things that we don't understand. They impart energy to their environments in ways we don't understand. So this is all not cosmology at some level, but it all matters, unfortunately. And the problem with all of this is there's very little scale separation between where you include gas and where you include star formation, feedback, etc., etc., etc. Right? So there's a very limited dynamic range where adding just gas helps. And so when people say they run a hydrodynamic simulation, yes, there's hydrodynamics in there, but it's not the pressure forces and the fact that there's a grad P term that's the problem. It's all of this stuff. And these all rely on subgrid models, and that's where all of the nastiness is. So just to show one example of this is from a fairly old paper now, but just to give you an idea of the effects. So this is plotting K again, so the last plot kind of cut off at K of 1, so this is extending on outwards. And this is showing you the difference between the power spectrum in the full hydrodynamics, etc. run to the same power spectrum if I just took a pure dark matter run and it didn't include any of that extra physics. And if you just focus on the solid lines here, the red line here shows you the effects of just including the hydrodynamics, and the green line shows you the effects of including all of the other physics. And what you can see is, once the hydrodynamics starts becoming important compared to the dark matter, the extra physics is even more important than the hydrodynamics, right? So there's almost no scale in which you can really kind of take baby steps towards this problem. You basically get thrown in the deep end of the pool. Because this is all nonlinear and because it's all feedback, that means there's extreme sensitivity to initial conditions and so on. So this becomes quite a difficult problem. So I'm going to mostly ignore the yuckiness of hydrodynamics for a lot of this talk and talk about what we've learned from the dark matter problem, because even there's a lot to talk about, and people can ask me about the hydro stuff later if they want. If you look at this picture, your eye is kind of drawn to these fundamental building blocks of this structure, which are these dark matter halos. And so if you look at this, this network is actually made up of a beaded filamentary network. So you've got all of these filaments, but they're made up of dark matter halos strung along these coherent structures. And so there's a number of questions you could ask, and which we know about in this distribution. You could ask, what's the number of halos versus whatever property you like, for example, halo mass? What's the spatial distribution of those halos versus whatever you want? And then what are the internal properties of the halos themselves? What's their radial profiles? Are they spinning? What's their structure, formation, history? So the first thing to notice is that from the simulations and from a variety of theoretical arguments, almost all of the mass resides in approximately virialized halos. And that approximately there, we'll come back to in a little while, the almost means within a factor of 2. So notice already I've gone from my kind of 0.1% VAO discussions now to talk about factor of 2 errors. The space density of halos depends primarily, or in fact, as far as we can tell, almost exclusively on mass. And I'll quantify that a little bit more in just a second. In the sense that there is a very large number of low mass halos and a very few high mass halos. So roughly speaking, the differential number density of halos scales approximately as m to the minus 2 times e to the minus m. That's a rough scaling, it's not exact, but it gives you a character, an idea of what this thing looks like. And then as time proceeds, the characteristic mass where you transition from the power law to the exponential increases, right? So little m is some scaled mass unit. And it turns out that this mass function is almost independent of cosmology when written the right way. And I'll show you what almost means, and I'll show you what the right way is. And we don't really understand why that is so. We have some theories that take that as a starting assumption, but we don't really understand why that is so. And it's a little bit disconcerting how little we know about this, given that mass functions are used all over the place in cosmology and galaxy formation and evolution and so on. So there's this wonderful plot from this recent paper by Bhattacharya et al. That I love, just because note the dynamic range in the figure, right? This is 10 to the 11 to 10 to the 16, 10 to the minus 9 to 10 to the minus 2, right? This is kind of amazing figure. This is the joy of log axes. And the points here show you, in body simulations at a variety of redshifts, and then the analytic lines are fits to those data, right? They have some theoretical prejudice putting into the fit, But as you can see, we can provide fitting functions to these relatively smooth curves reasonably easily. And you can notice the power law dependence, and there's a kind of rollover towards a more exponential dependence here. If I write this mass function, the number density of halos per interval in mass, as this quantity f, known as the multiplicity function, times sort of a characteristic number density, which I get by taking a characteristic mass density, the background density, and dividing it by a mass, and then using the conversion between this scaling variable sigma to m, then I get this functional form. What is sigma? Sigma is the variance in the linear theory density field when smoothed on a scale that would have encompassed a mass m if I'd done this in initial conditions. So I'll come back to why one would do that. This shows a variety of different numerical simulations in different box sizes and so on in order to show convergence. And then this line is basically the fitting function that passes through those data. And this is a redshift 0. This is meant to be a cosmology-independent writing of this. And so you can see that, as I go to redshift 1.25, the line is just missing the points. And that's showing there's a slight non-universality here. But, it's at this relatively small level given the dynamic range on this figure. And you can see that better in this blow-up plot down below. So this is from a paper by Jeremy Tinker 1 or 2 years ago. That's not the only paper that tries to come up with these fitting functions. Here's just a table that I took again from this Bhattacharya paper that just shows lots and lots of different fitting functions. And as you can see from the weird numbers that come in here, these are just fits to the numerical simulations. They run a numerical simulation, they have some flexible curve, and they fit the coefficients of that curve. In order to do that, this f of sigma is defined in this following way, such that it integrates to 1. This would be the condition that all the mass lives in halos of some given mass, maybe much smaller than numerical resolution, perhaps. And then there's ranges of which these fits are verified and so on. So in order to try and understand where this comes from, and in some sense the understanding precedes the numerical experiments, there's really two sets of ways of thinking about it. One is what's known as excursion set theory, the other one is known as peak theory. The excursion set formalism is by far the most popular theory, but I put theory in quotes here because it's not even a self-consistent mathematical theory, so it's not deserving of the full word. And the idea, the ansatz, the assumption that is made in these excursion set models is that the fraction of mass that is going to end up in halos more massive than m is related in some specified way to the fraction of the volume in which the smooth initial density field is above some threshold delta c. So you have to tell me how to smooth, you have to tell me what that threshold is, you have to tell me what related means, and so different versions of this excursion set differ in those choices. But nonetheless, that's the basic assumption. So there's no reason necessarily to expect that that's so, but observationally it does seem to be so. And this was an idea that was basically first put forward by Press and Schechter. You can write the mass function under this assumption. The mass function becomes related to the statistics of a random walk. And this was really first codified in this paper by Bond and collaborators in 1991 that solved a number of kind of problems with the original Press Schechter formalism. It's then been generalized to talk about different ways that you can relate the initial and final fields, spherical collapse. You can make various approximations to the elliptical collapse problem, mostly that become again fits to numerical simulations, and so you can see those in these early papers by Mo and White, Sheff and Tolman, Zhang and Lam, and so on. These people make different approximations to the problem of doing an elliptically collapsing or non-spherically collapsing halo. Both of these sets of approximations are then sort of justified by looking at numerical simulations. There's a big problem here with how to deal with the non-locality of the halo collapse, and this was actually recognized even in the very early works, and so it goes back to the early 90s. There's a long discussion in the literature about this, and people just don't know. I mean, it's kind of built in at some level to the excursion set formalism. The other way of looking at this problem is to take the statistics of your Gaussian peaks plus a model for halo collapse, be it spherical or ellipsoidal, and then count the peak statistics and relate those to the statistics of the underlying halos. And this was first really developed, the peak statistics were developed in this famous paper by Bardeen, Baum, Kaiser, and Zel'dovich, which has, I don't know, now 5,000 citations or some such thing. Almost all of them not for the bulk of the paper, but for a fit that appears in like Appendix F or something of that paper. And it's based on this brilliant work by Rice in 1944 and 1945, who studied one-dimensional Gaussian fields and used those as models of noise in communications devices, right? So this is an electrical engineering paper, and it was basically generalized to 3D in this famous BBKS paper. Then what happened was Bond and Myers, soon after this paper came out, like roughly a decade, generalized this using a model of elliptical collapsing halos, right? Given the Gaussian field, you can calculate anything you want. So if you want to calculate how elliptical a given peak is, or its probability of being elliptical with any given parameters, you can do that. If you have some model that then works out what a peak of a certain size and shape and curvature will collapse into, it's a straightforward problem then to relate your initial conditions to your mass function. And so that's what Bond and Myers did in 1996 in this nice paper called the peak patch picture, which then really didn't get developed very much further. And then there's a paper that will probably come out soon after Euclid is flying and around at the same time as the square kilometer array, which will solve all of these problems more carefully. Both the excursion step theory and the peak theory have some major advantages in that they allow you to compute the mass function from statistics of the initial Gaussian fields. We're just doing pure linear theory. So you choose a filter shape, you compute some integrals of the linear theory, and they will all differ in the different methods, but nonetheless there's some simple integrals. So you take the linear theory power spectrum, integrate it, plug it into some formula that's provided, and you get the mass function and various other quantities. Not all of the methods turn out to be self-consistent, but they all produce numbers, and for many people that's good enough. You'll find that they often have quite reasonable success for mass functions. That success is usually improved by the fact that they're often fit to the n-body simulations, and so you can imagine that they would do pretty well at the things they would fit to. They turn out to be less successful at things like the conditional mass function and merger rates and so on and so forth. There's nothing wrong with these fits per se. They're an extremely convenient way of summarizing a large amount of information in the simulations, but I will point out that you have to be very, very careful about extrapolating these things, because in many cases, the fits have been adjusted so that they no longer are derived from any underlying theory. So extrapolating some fitting function beyond its realm of validity, things can go horribly, horribly wrong. And that has bitten people in the past. So now if I turn from abundance to talk about the spatial distribution of these halos, one of the things you notice immediately is the clustering of these rare, massive dark matter halos all the way out on that exponential tail turn out to be dramatically enhanced relative to the clustering of just the mass itself. And this was an idea first realized by Kaiser and Astafiev. There's this absolutely wonderful paper by Cole and Kaiser in 1989 that if you have never read it, I encourage you to go and read it. It's one of these things where over the next few decades, different people would take one subsection of that paper and then write entire well-cited papers that would make them famous based on it. This is a truly remarkable piece of work. And then it goes on and has been developed and developed and developed, and I just kind of got a little bit sick of typing out all the references. So there's many, many, many references in here that have been dropped. So what I show here is the correlation function, redshift 3 and 4, for the mass, that's these blue points, and then for halos that are thought to host quasars, which are rare objects. So these here happen to be 10 to the 12 and 10 to the 12.5 solar mass halos, given by the 10 to the 12 here and the 10 to the 12.5 there. And you'll notice, just looking at this, that the clustering of the halos is 2 orders of magnitude stronger in this correlation function here than is the clustering of the mass. Right? So it's a dramatic enhancement in the clustering strength. Also notice that while the mass correlation function does show quite a few signs here of curvature, on this kind of stretch it's a little hard to see, but if I were to draw it up, it would be very obvious. This is a curving line. These are astonishingly well fit by power laws. And so the shape difference between this line and this line is actually quite large, even though it's hard to see with this kind of stretch on the log axis. So that enhancement is known as bias. The bias in principle depends on scale. It can depend on scale to quite large scales. But if you keep going to very, very, very large scales, then it becomes a scale-independent number. And often when people talk about the bias, that's what they mean, is this asymptotic value. And this bias depends primarily on halo mass or rarity, depending on how you want to phrase it. And in the simplest models, B is 1 plus u squared minus 1 over delta c, where delta c was that collapse threshold I talked about earlier, typically a number like 1.7 or so, and mu is defined to be delta c over sigma, this linear theory mass variance. For more accuracy than this, you tend to use an n-body calibrated fitting function, which tends to use the same kind of models, or 1 on sigma or something like that. You have to be aware again that the behavior at the extremes can depart significantly from the fitting functions, and that can be a cause of a lot of problems. So this is a similar kind of story to what we talked about with the mass function. Something interesting happened in the last few years, though, which is that numerical simulations are now large enough that we have large enough statistical samples to start dicing these halos into different bins. And people started to look at the dependence on things like the bias, on things like halo formation history, or halo spin, or halo substructure, or concentration, or so on. And you found dependencies on formation, redshift, internal structure, and spin. So the bias is not determined purely by the rarity or by the mass, but on other properties. And this was first realized in 2005 in this paper by Gao, although, like all good things, when you start looking back through the earlier literature, there were plenty of hints of it earlier on. So this just shows you kind of the mean before I split the properties up, and you can see that low mass halos tend to be, have a relatively flat bias versus mass relation. Nu again is delta C divided by sigma. Sigma goes down as m increases, so nu increases as mass increases. And so the bias increases as I get to these rarer and rarer halos. This dotted line turns out to be that formula I showed on the previous figure, so that's up here. SMT is Sheff, Mo, and Torman is a famous fitting function you can see falling much below the simulations. So the old dumb theory in some sense does better fit to the simulations than the new improved fitting function just as you move to very, very, very rare halos. And then this red line is a fit that kind of passes through the middle from the study by Jeremy Tinker just last year. This dependence on things like halo formation history and so on became known as an assembly bias, and I've taken these papers from Gao and White in 2007. Just look, for example, at the left plot. This is a plot B again as a function of this mu parameter. So this is more massive halos off to the right. And what they've shown is that they've taken the sort of the full halo sample, and this is that plot that we saw in the previous slide, and then they've broken it up into the upper and lower 20th percentiles of a distribution, in this case formation redshift. And it's such that the solid lines show the lowest 20%, and the dashed lines show the upper 20%. And so you can see here that things that formed at high redshift and low mass tend to be more highly biased than things that formed more recently at low redshift of low mass. And this became known as assembly bias. And the reason this is so interesting is that it's extraordinarily difficult to explain in the sort of standard excursion set formalism. And so it highlights again sort of the theoretical problems of the excursion set formalism. I'll try and sketch, roughly speaking, why that is. The mass function turns out to be a fraction of random walks reaching some absorbing barrier in this excursion set formalism. The bias is the dependence of the mass function on large-scale density, right? If I change the density in the dark matter by a certain amount, how much do I change the number of halos, right? What's the ratio between the number density fluctuation in halos and the number density fluctuations in the mass? So in this way of doing the random walk picture, that's what happens at the early part of the walk. Things like assembly bias and mergers and so on all come from conditional probabilities, which is I start at some place, I know I cross some intermediate barrier, what's the probability I end up crossing the threshold later on? But once I have a conditional probability and I know that I cross this point, it doesn't matter what the large-scale bias was at that point, right? I've conditioned that dependence out. And so assembly bias is very hard to explain, next to impossible to explain in this picture. It introduces non-Markovian nature in the walks. It turns out to just really break the whole idea. And so there's a fairly long literature pointing out that this is very, very difficult to explain in this picture. Simulations really didn't help matters. They robustly saw this effect, but they didn't point much guidance towards what this might be due to. But I think we now understand that a lot of this assembly bias is really just due to things that we should have known had we read BBKS a little bit more carefully. It's just a simple consequence of nonlinear collapse from Gaussian initial conditions, and the argument is given in this paper, and I'll just run you through a shortened version of that. So I'm going to deal with the two limiting cases. The intermediate case is a little harder. So assembly bias at high mass and at low mass turns out to act very differently, so let me run you through those two cases. It turns out if you just go into the simulations and look, later forming high mass halos are more clustered than a typical halo of the same mass. It turns out that concentration of halos also depends on when it formed, and so this statement is often framed not in terms of formation, but in terms of concentration, but I'll deal with it in terms of formation time. It turns out that very massive halos collapse almost spherically from the extremely rare peaks in the initial conditions, and this was known even by Zel'dovich back in the 70s. And that means that this collapse is reasonably explained by the spherical top hat collapse model, which is a famous model you can find in almost all undergraduate textbooks on cosmology. It turns out for a Gaussian field, the bias depends not only on the peak height, but also on the curvature, where the curvature I'm defining here is the run of the mean density of that peak with radius or with enclosed mass in the initial field. So this thing is often called S in the literature. And peak curvature basically translates into environment, because if I'm sitting on some peak of a given height and I want to know what's the background density in which I sit, then by Taylor's expansion, the background is related to the peak height plus basically the derivative of that smooth density with mass. And an interesting thing about Gaussian random fields that you can derive in about half a page of algebra is that peaks with a smaller absolute value of the curvature, right? The curvature around a peak is negative, so the smaller absolute value have larger background densities. And so if you write b minus 1, if you just wrote it in terms of the peaks and I integrated over all possible curvatures, you get that expression that I showed you previously. But if I actually include the curvature, so here nu is the peak height in units of its variance, x is the peak curvature in units of its variance, and you see there is this dependence that depends on the cross-correlation between peak height and curvature, and on the actual value of the curvature I measured on the actual value of the peak height that I measured. So this is a very simple thing. You just have to invert that 2x2 matrix and write out just doing Gaussian integrals. If you actually look in the simulations, you find, stunningly enough, the simulations can do Gaussian integrals as well. So this shows the bias as a function of d log delta d log m, taken from a series of simulations. The points of the simulated simulation numbers, the solid line is that formula I just had written down previously. And so what you find is that the dependence of halo bias on peak curvature basically matches what you get just out of Gaussian peaks, right? So the nonlinear collapse isn't doing anything to alter, at this very, very high mass n, anything to alter that. Now, remember I said that halos form when the mean density goes above some critical threshold. So you can think of the curvature of this peak as being the assembly history, right? As I go to smaller and smaller masses, I'm scaling my way up that peak, and so depending on where I'm crossing various thresholds, that tells me what things are collapsing as a function of mass. And in the simple case of this power law cosmology that we did here, it turns out that d log delta d log m just becomes d log m d log scale factor to the minus 1. And you can actually go in and look at the formation histories of these halos and find that this mapping is extremely good. And so this tells you that the bias is dependent on the formation history in just the way you need to explain the fact that these halos are, early forming halos are more biased. The low mass case is slightly more interesting and slightly trickier. It turns out that the assembly bias swaps sign. So previously it was the early forming halos that were more concentrated, more clustered. Now it's the oldest, most concentrated low mass halos that are more than twice as clustered as the youngest halos of the same mass. And that was the plot that I showed you earlier. But if you actually go look more carefully, what you find is that the youngest 80% of halos have a bias which is just 1 minus 1 over delta c, which is that asymptote of about 0.4 that we saw on all the other plots. So the youngest 80% of halos behave exactly as expected from the normal, in quotes, bias theory. The oldest 20% of low mass halos have a bias very close to 1. And that kind of makes sense. These things are extremely low mass and they formed very early. So they're just acting much like the dark matter is acting, right? They're just moving around just like test particles in this flow. So not surprisingly, as the structure grows, their bias is driven to 1, meaning they act just like the dark matter, they become unbiased. And so what you find is that most of these guys are actually associated with nearby high mass halos. And if you look at what's happening, you can go into the simulations and show that these things were things that formed early and were on their way to become a massive halo, but they formed right next to something even bigger. And the something really bigger, the big neighbor, kind of took the mass that would have accreted onto them and left them. They formed early, but then their growth was shut off. And so their growth is stunted by the hot environment of their massive neighbor. So they formed early, they're in an overdense regime, and they've been acting like a test particle. And so it's this split between the 80% of things doing what you expect, and the 20% of them that have a bias that's twice as large that gives you this interesting assembly bias. So let's talk a little bit about the actual halos now. We've talked about their clustering, we've talked about their abundance. Here's a plot taken from a simulation that we'll come back and look at over a while. Dark matter halos are generally triaxial spheroids. They're quite elongated, roughly 2 to 1. That's where we normally approximate them as spheres. They're more elongated at smaller radii, larger redshifts, and higher mass. And there's twisting of the isotones or the isodensity contours. They're quite complicated beasts. They're approximately in virial equilibrium. I'll show you a plot of that in just a second. And as you can see from this, all of the material that's plotted here is cut off to be material that's above 100 times the background density. And what you can see very clearly here is that this is clearly an object falling into this halo. This is another one falling. If I had plotted down the lower density contrast, these things would come out like filaments, pointing off of this halo, and this would have been embedded in the filamentary large-scale structure. And you can see that this halo is clearly aligned with these sorts of infall directions. And so you find lots of alignments of halos with the cosmic web around them. That's not surprising because the material which is feeding this halo is flowing in along these filaments, and so you would expect that kind of behavior. behavior. Similarly is true of the velocity field and so on, as Joanne mentioned in her talk. The average mass accretion turns out to be exponential, and there's a simple argument based on the EPS formalism which allows you to prove that. You find that the mass mass growth is proportional to the mass with some very, very slowly varying creep factor, which is a very low power of the mass. So we kind of understand this sort of exponential mass growth, although for any individual object, it's very, very punctuated as individual halos falling on top of it. So when you average over many halos, you get this exponential accretion. And there's a spin parameter. These guys are all spinning. Their dimensionless angular momentum in terms of energy is about 5%. And this spin parameter grows pretty significantly when you have a major merger, meaning that something big comes in and slams into your halo, and it slowly declines when you're accreting objects just kind of more or less spherically around you, as might be expected. This just shows a plot, one of many you can find in the literature, showing the dynamical state of the halos. So this shows you the velocity dispersion as a function of radius in terms of what I refer to here as the top hat virial radius, that is the virial radius that you would have got using spherical top hat collapse. And this shows you the mean radial velocity in radial shells. So what you can see is interior to the halo, the mean radial velocity is about 0. Then at some radius that is approximately given by the top hat virial radius, the velocity field becomes negative. That is, things are falling into the halos. This is the infall region. If I were to extend this plot all the way out to the right, you would actually see these curves turning around and going back up as you move out with a Hubble flow, and of course things are flowing away from you. And so you have something that is almost isothermal and quite well mixed in the interior regions, and then have an infall region and then finally an outflow region. So you have two zero velocity surfaces. If you choose a mass definition which puts the mass somewhere between those two zero velocity surfaces, this mass function turns out to be approximately universal. If you do something interior to those surfaces, the mass function has significant cosmology dependence, so there's a reason for actually looking at the dynamics. You can see significant substructure here. It shows up even better on the computer screen, but there are hundreds or thousands of dark matter subhalos interior to this. And you actually find, you can even see, here's clearly a group that is falling in until eventually hit these two things. There's two massive subhalos in there. Notice that the group itself has lots of subhalos. There's coherence in the velocity structure between the subhalos of this group and the group motion. This whole thing is going to move in and gradually move around. So the idea that these are somehow incredibly well mixed is a little bit misleading. There's a lot of substructure in dark matter halos, as I'll come back to. However, if you ignore all of that, and you just spherically average, just sit in the middle of that halo and plot the mean density averaged over many, many halos, you find plots, mean interior density versus radius, that fall on this functional form, which has become known as the NFW profile, the Navarro-Frank-White profile, which is just a broken parallel running from x to the minus 1 to x to the minus 3. There's two free parameters in principle in the NFW profile, although it turns out that the two are related, so you really get a one parameter family, but there's scatter in that relation, and show this shaded line shows you roughly the degree of scatter that's expected in that relation, and the error bars show you the variance when I take all halos of these given masses in the simulation. You can see it nicely matches the scatter that's observed. That's not too surprising because the scatter was measured from simulations, but at least it shows that we can do the appropriate error propagation. This concentration parameter, which is defined to be the virial radius divided by the scale factor, is a function of the mass, and so my two-parameter family becomes a one-parameter family. In the sense that more massive halos are less concentrated, it turns out, of course, that these halos live in a beaded filamentary web. For a star, it's pretty obvious where the surface is, more or less. For a halo, it's completely not obvious where the surface is, and so it's totally unclear what you mean by the mass of a halo. This means that all authors come up with at least one definition. Several authors have used 3 different definitions in a single paper. Since this is all the mass, they're all referred to as M, and you're meant to know by context which M they mean. Just like M, depending on definition, C depends on definition, so sort of caveat reader, if you're looking up fitting functions, try very hard to at least get a set of fitting functions that are consistent. This is like Fourier transform 2-pi conventions. Doesn't matter which one you choose, but don't swap halfway. The concentration is a very weak function of mass, scaling roughly as mass to the minus 0.15. It's not exactly a perfect parallel, there's breaks and so on. And there's a very large log-normal scatter in C. So halo by halo, the concentrations go all over the place. But if you average over thousands, you get a nice simple relation. Physically, we kind of understand, roughly speaking, why there is this division, and it's actually also related to the halo accretion history, which we also understand relatively well from simulations. The inner kind of r to the minus 1 cuspy part of the halo forms pretty early, and then this RS thing stays roughly constant in physical coordinates, which means that it's sort of, in some sense, shrinking into the moving coordinates. And then any subsequent accretion is kept away by the angular momentum barrier, right? Things coming in from, with some impact parameter just can't get very close to the center. And so that builds up this kind of outer envelope, this sort of r to the minus 3 type envelope. And that tells you that the concentration should scale roughly as 1 plus z to the minus 1. And that is, when averaged over a sufficient number of halos, that is roughly what we see. Now, the NFW form is by far the most popular form. You can argue with the broken power law in some sense. But there's many, many other forms that do as well, if not better, fitting what we see in the simulations. There's a so-called generalized NFW that makes minus 1 and minus 2 variable, right? So there were two exponents in there, x to minus 1, 1 plus x to minus 2. So you can call one of those alpha and one of those beta, and then they can be free numbers, and that's known as the generalized NFW profile. It's a very nice form known as the INASTO profile that people who do galactic structure will probably recognize as the kinds of models that people often fit to the projected surface density of galaxies. But here I'm thinking of fitting it actually to the three-dimensional density in a simulation. So it's an exponential of a power of r. It has, again, a number of parameters in it that are related to each other. And this n, the 1 on n in the exponent here, is typically in the range kind of 5 to 10. I put this in. If you actually plot it, it does just as good a job of plotting the, fitting the data, the numerical data, as do things like the NFW profile. The interesting thing about this is as I go to r of 0, of course, this goes to rho of constant, and so this has no cusp. And yet this fits the n-body data just as well as the NFW profile. Right? So it's actually quite hard to tell the difference. Where all of these profiles come from has been a very, very long-standing puzzle, and it's one where it's even hard to phrase the question very well. Because as I'll point out a little bit later on, this NFW profile is transitional. So you can't really appeal to equilibrium in some sense, given that it's all going to change. So it's some quasi-equilibrium behavior. But I think there's this really interesting paper by Lithwick and Dalal that came out kind of late last year, building on earlier work by Fulmer and Goldreich and Götzinger, that I think has made really dramatic advances in our understanding of why halos look like NFW profiles. And it's not that there hasn't been a lot written on this subject, but I think there hasn't been much actual linear momentum or thermal motion in terms of us getting ourselves confused. But this paper, I think, is actually going a long way towards telling us what the hell's going on. One of the problems in that understanding is that at some level, it does rely in crucial steps on numerical simulations, highly simplified, highly idealized ones that tease out what's going on. But it's still a semi-numerical, semi-analytic explanation. The other thing to bear in mind from all of this is the NFW profile itself is actually transitional. If I really live in a dark energy dominated universe, which sometimes I do, this r to the minus 3 outer slope is coming from the fact that material keeps raining in on the halo. And so it just keeps building up this kind of extended envelope. But accretion will stop in a dark energy dominated universe. If I wait a few more Hubble times, there won't be any further accretion. And this was explored in this nice paper by Michael Lucia, Gus Everett, Fred Adams a couple of years ago. And what you find is that this r to the minus 3 slope actually gets exponentially truncated at large radius. So you end up with a very different looking halo profile. So if we were around a few Hubble times from now, that's my goal, then you find that you wouldn't be trying to explain the NFW profile at all. You'd be trying to explain the Lucia profile, which looks qualitatively extraordinarily different. So that's been one of the big problems with explaining the NFW profile, is figuring out what it is you're actually trying to explain, if it's a transition state. Let me finish up. I won't spend very much time talking about this at all. We'll hear a little bit more about it, I guess, from Andrew Wetzel later on this afternoon. I plotted, showed you those pictures in which you can see a lot of substructure within those dark matter halos. And the existence of this substructure is, of course, a very generic prediction of hierarchical theories, because in hierarchical theories, matter forms bottom up, and I start with very small structures that are accreted and merge into larger and larger structures. Those structures are not all disrupted, although a large number of them are. And so the virialized regions of dark matter halos contain subhalos. The virialized regions of the subhalos contain sub-subhalos, and it circles all the way down. Right? There's this whole hierarchy of things. A subhalo I'm defining here as a self-gravitating bound clump of dark matter, easy to do in a simulation. In modern galaxy formation theories, this is where all the galaxies live. So in modern simulations that include star formation and feedback and cooling and so on, every galaxy lives inside a subhalo. I'm not sure we can say the opposite, that every subhalo hosts a galaxy. But still, these subhalos account for about 10% of the halo mass. So that's a subdominant component, but if we're talking anything to do with precision cosmology, this is an important component. That's slightly more than the amount of mass that a galaxy contributes to a cluster of galaxies in the observed universe. Right? All modern theories of galaxy formation believe that luminous galaxies form by the cooling and condensation of gas in subhalos. So in some sense, the subhalos form our link between observations and the simulations. If you look at the actual subhalos themselves, their density profiles are quite similar to that of halos. They look sort of like a broken power law, except that they can be and frequently are truncated, especially if they're in very massive dark matter halos which have strong tidal fields. You get straight tidal truncation, tidal stripping. Subhalos track the dark matter closely in terms of density and velocity. They're not absolutely perfectly unbiased, but they're relatively unbiased. There are trends of central concentration and velocity bias with the ratio of the subhalo to host central mass. Things that are more massive, experiencing more dynamical friction and so on, are having more velocity bias compared to things that are very, very low mass, which behave much more just like an unbiased tracer of the mass field. All of these statements depend crucially on how subhalos are selected, and if you thought the situation with halos was bad, the situation with subhalos is a complete nightmare. And if you want to waste several days having people bitch at you about the joys of subhalo selection and so on, ask either Andrew or Joanne in the audience about how much fun it is to select, track, and play with subhalos and n-body simulations. What's interesting, though, about all of these subhalos, and this is confirmed by a wide body of work, is that if I go either up in host mass or down in subhalo mass, the number of subhalos above a given mass grows linearly with the host halo mass. Now, how far you have to go in mass ratio before that sets in, this sort of plateau, as it's often referred to, is set by dynamical friction and the fact that the mean density of collapsed structures is roughly 100 times the background density. So that's almost a tautology, a definition of what forms the virialized region of a halo. As you know, the typical time of a characteristic time of an object goes as 1 on the square root of its density. So halos have a dynamical time roughly 1/10 of the Hubble time. The dynamical friction scale goes as the typical dynamical time times the mass ratio of the object you're in to the object you are. And so that means you can live a Hubble time if you're 1/10 the mass of the host halo. If you're more than 1/10 the mass of the host halo, you will experience significant dynamical friction and plunge to the center to die a horrible fiery death. And so that's what sets this plateau, roughly a factor of 10. But suppose I'm less massive than that, then I can orbit in principle forever, which means a Hubble time. And so if you look below, in this MSAT much less than M host region, subhalo mass function and the halo mass function are scaled versions of each other. Right? So remember I said the low mass slope of the mass function is roughly m to the -2. If you plot the number of satellites per host halo as a function of their satellite mass, it looks like m host over MSAT squared, again asymptotically. And so you have this situation where the destruction rate of halos and the infall of halos are roughly in balance. It's not that any given subhalo lives forever. It's that the accretion rate and the destruction rate are almost perfectly balanced. This leads to all kinds of interesting coincidences which people have noticed in various guises over time, but it is a robust prediction of the dynamics. The exact form of that is unclear, given that there's many things that should be breaking this sort of similarity. All right, let me finish up here just by thanking everyone. First of all, the participants, several of whom were even here at 8:30 in the morning. The other lecturers for teaching me a whole bunch that I'm glad I learned. Of course, the organizers for putting things together and the staff for making this such a pleasant stay. I got a lot out of this meeting, and I hope you did too. Thank you very much.
So it's time for questions, comments, remarks, please.
I have a question about your point that the halo mass function is cosmologically independent, specifically because the delta you assume is cosmologically dependent.
You're referring to this delta C, the threshold density?
Yeah.
There is a weak, well, I'm not entirely sure how to answer that question in the sense that, in the fitting functions for the n-body simulations, which is what 99.9% of the community use, delta C is not cosmologically dependent because it's a parameter of a fitting function, in which they take to be constant. If you believe the spherical top-hat collapse model, which there is zero reason to believe, right, because we know that's not how halos form, but if I did that, then you're correct that, for example, in a dark energy dominated model, the standard way of calculating this, there's a mild dependence on lambda or on the dark energy density, delta C. It's pretty small. On the other hand, delta C comes into an exponential. So I think the way most people deal with this is that they motivate things by using the spherical top-hat collapse model, and then to get any numbers, they go and they look at a simulation and they fit a line through the points. And almost everything that I know about any one of these fitting functions has taken delta C to be constant, and has some throwaway line in the footnote of the first paragraph of the appendix that then gets dropped before publication that says we understand delta C has some cosmology dependence, but for simplicity we'll not do this.
These subhalo properties you mentioned in your last slide are the result of n-body simulations, or
They're observed in n-body simulations, yes.
Okay.
So they're the result of many decades of n-body experiments. They are to some extent understood, but not very well. They're also seen in simulations where you have hydrodynamics and star formation and cooling and feedback. In gross detail, the differences between including the extra physics and not including the extra physics are not very dramatic. So these things seem robust to the inclusion of additional physics like star formation, feedback, and cooling. It's hard to make any completely accurate statements since none of the models that include star formation and feedback and cooling match observations, since none of them are right. It's hard to know whether the one that eventually gets it right will match the n-body simulations as well as the ones that aren't getting it right, but are trying to. But it does seem to be quite robust. So several of the properties can be understood with simple analytic arguments based on things like dynamical friction. We know a lot about how the halo population evolves with time, so we know in principle how things accrete onto the halos. So I now know how they orbit within the halo and I know how they accrete. So you can see that you can kind of put together a chain of logic which matches what we see in the simulations. There is slightly the worry that if I'd seen something different in the simulations, I would have come up with a different chain of logic that matched that too. So the uniqueness is unclear. But I think there's no missing physics problem here. You kind of understand the mechanisms. And then certainly, if you go and look in clusters of galaxies, they contain lots of little subhalos, right? Many of them have names. So qualitatively, at least, it's getting things right. If you just do a simple matching one-to-one of subhalos to galaxies, you can predict an awful lot of things. Predict an awful lot of things that we know about the observed galaxy distribution. It's clustering luminosity functions. Luminosity functions is a function of density, is a function of redshift, is a function of luminosity threshold, and so on. Really quite well.
More questions? Okay, not we thank Martin White.